So let's just continue. We formulated and proved the one deviation property, which is a simpler way to state B in a subgame perfect equilibrium. So I remind you that the definition of a subgame perfect equilibrium is that, well, it's also, you can also have two options which are equivalent. One is to state a claim that in each subgame there is a Nash equilibrium. Another is to claim that for each player and for each state where this player is the player who acts, this player has the optimum strategy in this subgame. Now look at the second option. The second definition speaks about a player having an optimum strategy in a given subgame. Now the one deviation property is basically the same. It claims that it's enough so to look at possible deviations only at the first state of this subgame. As long as there are no deviations which help, that's enough. We don't need to think about other deviations. So in a finite horizon extensive game with both information, profile S is a subgame perfect equilibrium if and only for each player I in each state V where this player acts, the utility that this player obtains in this subgame cannot be increased by any deviation which differs from the original strategy only at this state. As long as such a deviation does not exist, that's enough to claim that there is no deviation in general. As long as no player, no vertex, but player X, there is a deviation like that, it's enough. And it's necessary to have a finite horizon to apply this. I remind you that we needed that in the proof, and maybe we'll see an example actually when it doesn't work, because we know that our proof doesn't work when the horizon is not finite, but maybe we'll see an example other tutorials that it's actually not true when the horizon is not finite, generally speaking. But now let us continue to prove the existence of subgame perfect equilibrium, and that's the famous Kuhn's theorem. So we are now ready to constructively prove existence, and basically the construction, as we saw already, is backward induction. 1 second, please. Which generalizes show whether now it should be. Hope you see now in the slide. I should somehow moved it too much. Yeah. Okay. So this backward induction, which generalizes Zermelo's algorithm. I remind that Zermelo's algorithm looked at each state and basically said, okay, if a player can choose an option, the acting player can choose an option that will make it win. Of course, it chooses such an option. If it can only choose, if it cannot choose an option, there is no option where it wins, but it can choose an option where it gets at least a draw, then it chooses that option. And of course, if there is no option either for that or for that, then it just has to choose some other option. And that means that the other player wins, because each option has been already inductively labeled, backward inductively labeled, by one of the three options. Now that was for the case when you had only three options: 1, 0, minus, 1, 1. Excuse me, 1, minus 1, minus 1, 1, or 0, 0. Now, in our case, we have arbitrary numbers. Does not have to be that you have only like ones and zeros. So it's a bit different. It's not much different. So we do need this finiteness, because in order to have a maximum between among arbitrary numbers, you do have to know that we have finiteness, not only of the length, so that the induction will actually cover all the tree, but also that the number of options is finite. So we therefore require a finite game. So it's a stronger requirement than a game with a finite length. I mean, a finite height of the tree. And with the theorem is as follows: a finite extensive game with perfect information. Well, all the games in this lecture are perfect information. Has a subgame perfect equilibrium. So that's a very nice theorem, and that's not so hard. So we construct this equilibrium. We construct strategy profile by induction on the length of the longest path, on the length of the game. And while doing that, we also associate each state with the outcome under this constructed strategy. So the base of the backward induction is a leaf. So for any leaf, there is nothing to define, no action to take. So we just define, well, depth is 0 if and only if it's a leaf, and we define, so height of the length of the tree is 0 if and only if that's the length of the subtree is 0 if and only if it's a leaf, and we define R to be this leaf. So that's the outcome. Now, the step assumes that we have already defined R and S for each V. Actually, I should say R and S. Let's once define R and S. Now the S is the strategy, and it tells what the player who acts does. So S in this case is of the player who acts at this V. So we assume that we have defined R and S. This P should be in the subscript for each B, such that the length of the corresponding subtree of this V is at most K. And then look at any V such that the length of the corresponding V star, that the length of the corresponding subtree, gamma V star, this length is at exactly K plus 1. This is the induction step. And since it's K plus 1, it means that the length of every child is at most K. It can be smaller by the way than K, but it's at most K. There is exactly one, actually at least one child where it's exactly K, because that's required for the length of this V star to be K plus 1. But some children may have a strictly smaller length. I mean the tree height, that's the length of the maximum path. The length of the maximum path is the height of the tree. So, by induction hypothesis, the R, the outcome of the V star, is defined for any such child V star because its length is at most K. And of course, the S is defined. And that's defined as the outcome under this constructed S for every such child. So now we define the what the action strategy S tells the agent who should act at V star. So the S of P V star will be the best for that agent I, or I should have, yes. Yes. I is the agent who acts. The best from the point of view of this agent of all the outcomes, which will be under the strategy we have defined at the children. So we look at what happens each of the possible children, and at each of the possible children, we look at the outcomes from the point of view of the utility of this PV star, and we maximize that utility. So you choose the child maximizes your utility under the assumption that they will continue acting by this S. And then, of course, we also define the R of this star as the R of the R of the chosen. So you have chosen of the R of the chosen child. So this S of this star tells where to go, and their R is already defined because the depth is at most k. So that's the outcome which will take place because that's where we go. So the fact that R does what it should do shows the outcome. Simply is true at every point, so you can inductively prove that. We can also claim simply that this induction basically maintains this what's the word for that? Wow, forgot the word. The induction maintains the something that always exists, does not change, not irrelevant, but I forgot the word. I'll tell the word when I recall it. But basically, they have defined the strategy S and R, which always tells us what is the outcome on the S. Now, we claim that this defined S is a subgame perfect equilibrium. Why? Because of the one deviation property. So at each point, we have defined S such that it's the best thing for that player at this point. Therefore, there is no deviation that only deviates at this point and improves something. Because at this point, given that you continue as you've defined, that's the best you can have. Therefore, by the one deviation property, that's a subgame perfect equilibrium. So we have defined by backward induction a subgame perfect equilibrium. Now, some remarks. The backward induction is indeed nice because it allows us to have this. It's basically an algorithm. It's quite a natural thing, I think, how people can analyze what happens. Now, because unless the tree is extremely huge, and then you may need to resort to some heuristics, somehow prune some parts of the tree. But anyhow, that's the best thing. That's something you can reasonably say is the best thing when the tree is reasonable, is not too huge. Now, the second remark is that Kuhn's theorem is a generalization of Neumann's theorem. Von Neumann's theorem, it basically does this Zermelo. It basically runs the Zermelo algorithm. Actually, maybe the Zermelo algorithm is only defined when we have is defined on the general tree and not on this victory, loss, or draw tree. I don't know. It does not matter how you call it, but it can be seen as a generalization of this algorithm for finite games. Now, it's important, however, that we do constrain the algorithm for finite games. There, when we spoke about von Neumann's theorem, it was enough that the games, that each path was at most something, that the longest path was bounded. Now, when the games are finite, we can see that theorem we've just proved as something which is indeed strictly implies the theorem for victory, loss, or draw games. Actually, in the book by Osborne and Nurbuchen, they prove only this one, the theorem we've now proved. And then for finite games, they simply say as follows. What they say is that a subgame perfect equilibrium is in particular a Nash equilibrium. And in a zero-sum game, in a victory loss draw game, which is zero-sum, there is a unique Nash equilibrium pair, and it's guaranteed under the max-min strategy. So the existence of subgame perfect equilibrium, which implies, of course, the existence of a Nash equilibrium, because subgame perfect equilibrium is always a Nash equilibrium. It means that we can always guarantee. You can guarantee this equilibrium value. So it implies that at least either one player can guarantee to win, the other player can guarantee to win, or both can guarantee it is a draw. Now, when every player is finite, but the game may be infinite, it can happen. Then, let me actually show you that then, what we proved So what proved is that for a combinatorial game, we have one of three options, and the definition of combinatorial game is that every play is finite. Even the largest, there is even no requirement that there will be some bound on the longest play. It can be that there is a play for every natural number. So it can be that there is no longest play. But the reason that we need to exhaust the tree by this induction, every play has to be finite. Now, that was enough there. Now here, we need a finite insufficient tree. But can we basically generalize our proof when we have a game with every play is finite, which is a combinatorial game? Yes, for that case, for the combinatorial game, or in other words, if we know that it's only a victory, loss, and draw game, we can generalize this proof because we need in the inductive step that we will be able to tell which action is the best. That's what we do here. Now, in general, we can have no best action if there is an infinite number of actions. But if the values eventually of these R's are only 1, 0, minus 1, even if the number is infinite, we can have the best action. So this proof can be generalized also for this case of maybe infinite games when the length of the path is known to be finite. So for finite games, this theorem is strictly stronger than von Neumann's theorem. It strictly implies that for infinite games, where we just know that each path is finite, each play is finite, this theorem does not by itself imply that von Neumann's theorem, but we can just easily generalize the proof so that it will imply that theorem. Now, another thing is that this theorem proves, of course, existence, but not uniqueness. And it's true that there is no uniqueness, not even uniqueness of pair, as we will see now in an example. However, if no player is indifferent between any couple of the outcomes, then the subgame perfect equilibrium is unique. Now, why? Because then, at each stage, there is only one option to act. So there is no, if you want to be a subgame perfectly proven, you have to do the best thing for the player at the moment, for the acting player. If there is no couple of outcomes where at least some player is indifferent, that at each stage you have exactly one best option to act. You have to do it. It has to be, because otherwise it's not a subgame perfectly proven. And then there is uniqueness. But in general, there is no uniqueness, as like in this example. And of course, in this example, we see that there are many players who are indifferent in several outcomes. For example, player 2 gets 0 in this outcome, in this outcome, this outcome, this outcome. Actually, no outcomes besides this one. Actually, I think that maybe even Ron is that a wrong depiction. Let me see. Yes, it's a wrong depiction. But it's still true that it's that players, of course, are not always, they don't always care which outcome takes place, but it's a wrong depiction of that. It's 2, 0. Fix that and yes. Okay. So here it should be 1, 1. But still, player 2, for example, is indifferent between these and these options. So it's reasonable that you can have multiple subgame perfect equilibrium, and you do, as we shown. So this example is actually a nice example also to see the distinction between Nash and subgame perfect. So look at the following example. Consider allocating two identical and divisible objects between two players. So you just need to decide who gets how many objects. Two identical indivisible. So indivisible means that you can only give one object, no object, one object or both objects to a player. And they're identical, so you don't need to count how many objects you give. You don't care whether you get object 1 or object 2. So there is an option of giving any number of objects to each player, such that it's always non-negative, integer, and the total is at most 2. Of course, you can just not give players anything. And the allocation goes as follows. That's the process is as follows. So player 1 decides how to allocate, and she offers player 2 to say whether player 2 agrees. So player 1 says, okay, I get 2 objects, you get nothing. Then player 2 says yes or no. If she says yes, then that indeed happens. If she says no, nobody gets anything. We have free disposal, so we don't have to use all the objects. Another option, player 1 can offer. We see player 1 always offers how to allocate both items full. So player 1 does not say, okay, let me you get one object and you get nothing. You simply assume that player 1 always tells 2, 0, 1, 1, or 0, 2. So the second option, if player 1 says, let us get each one object, player 2 can say yes, then that's what happens. Or she can again reject that, and then nobody gets an object. And the last option is that player 1 can say, okay, I get nothing, you get both objects, and even then player 2 has two options. Yes, and then that's what happens, or no, and then nobody gets nothing. So there are many Nash equilibria, because let's see actually why those are Nash equilibria. So the strategy of player 1, let's see what one of the possibilities to construct it is to look at what is the optimum reply of player 2 on strategy of player 1 to 0. So player 2 can tell, okay, I can tell everything. Or you know what, let's look at a different way. What player 2 can, first of all, what does player 2 have to tell? What has to be the strategy of player 2? In order for player 1 to have a motivation to tell to 0. So first of all, if player 2 says yes to 2, if the first option gets yes, then player 1 has this motivation. Does not matter what happens then. Player 1 is motivated to tell to 0 is the best option if player 2 says yes for the first option. So it can be yes, 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 or yes, yes, no, or yes, no, yes, or yes, no, no. In all the options, player 1 is motivated to tell to 0. Now, in order for player 2 to be motivated to answer that, then it's always an optimum option because player 2 does not get anything anyway. So she can do whatever she wants. For all of those as a strategies of player 2, they are all best responses to the strategy of player 1 to 0, because the strategy of player 1 to 0 does not let player 2 get anything anyway. So these are all best responses. Now, another option player 2 can best respond, and still the player 1 will have will be able to say that to 0 is the best response from her point of view, is when player 2 actually tells no for to 0, but then she leaves no option for anything better. So if player 2 says no to 0, but all the other options get no as well, so to 0 in particular is the best thing because nothing, player 1 cannot get anything for this action of player 2, n. If player 2 says no to 0, it can be n, y, and y, excuse me, no. I said something wrong now. If I say no to 0 and no to 1, then does player 1 has no option, because then player 1 can only get to deal with 0, 2, so she does not get anything. So when it's n, or n and y, or the first two options are rejected, then also player 1's to 0 is optimal for her. And now, from the point of view of player 2, as we said, anything is optimal when player 1 plays to 0, because player 2 does not get anything as a result. So these are all the options when player 1 offers to 0 for an Nash equilibrium. These are all the options. Now, let's move to all the options when player 1 offers 1. In that case, so what are the options that player 2 can do so that player 1 is optimal here? First of all, of course, player 2 has to reject to 0, because that otherwise that would be strictly better for player 1. So player 2 has to play n into 0. It has to play n into 0. It has to also play yes. One second, does it have to play yes? Aha. Yes. It has to play n for 0, that's clear. Now we have therefore n1 y. Now why don't we have n? Now now it's easier to start with that option. I just need to see how to reduce the number of options so that we won't have this combinatorial explosion. So since player 2 now, let's look at what player 2 may do. Since player 2 needs to be optimum for anything that player 1 offers, player 2 no. Player 2 has to be optimum for 1. It therefore may not reject y1. Otherwise, it would not be an optimum reaction of player 2. So the second option has to always get yes. So therefore, it indeed has to be no on the first place. It has to be yes. It has to be yes on the second place always. Otherwise, it's not an optimum reaction of player 2 to 1. Now, then let's go third. it has to be yes at the second play. It has to be no in the first place, because if it's not the case, then player 1 would, of course, play 2-0. So it has to be NY in the beginning. And the second option is actually free. I mean, it's arbitrary. It's not determined in the sense it's free. So it can be yes or no. In any case, both in NY1 and NYN, player 2 is best responding to 1-1 because it accepts it, and player 1 is best responding to this offer because the best in this offer that player 2 accepts is yes. It is the 1. 1-1. So that's why. So let me explain it again. Player 2 has to say yes to 1-1 to be optimum. Player 1, in order for that to be optimum, player 2, in order for player 1 now to be optimum, player 2 has to say no to 2. So NY are necessary here, but that's already enough because NY in the first two parts of strategy of player 2, when player 1 plays 1-1, guarantee that player 2 is optimizing simply because it is Y, yes, and player 1 is optimizing because when you have NY, player 1 is optimizing. It's optimum for player 1 to say 1-1. And the last question: what are the Nash equilibria when player 1 plays 0-2? Well, first, player 1 would not be making anything. It would not be optimal for player 2 if she rejected that option, of course. So player 2 has to end with yes. Now, it would also not be optimal for player 1 to offer that unless player 2 rejected the first two options. So it has to be N and Y. No, yes. And then indeed player 2 is optimizing the degrees 0-2, and player 1 is optimizing because when player 2 accepts only 0-2, player 1 can do whatever she wants. She's optimizing. So these are all the possibilities. We just exhaustively looked what are the possibilities when player 1 plays 2-0, what are the possibilities for Nash equilibrium when player 1 plays 1-1, and what are the possibilities for Nash equilibrium when player 1 plays 0-2. And these are all the possibilities for Nash equilibrium. Now, what are the possibilities for subgame perfect equilibrium? Among the Nash equilibria, they have to be Nash. They are much smaller because here we require that player 2 actually does the best thing for her when she acts. It's not only that her strategy is the best response to the strategy of player 1, but whenever she actually acts, it has to be the best thing for her at this moment. And that's not always the case. So, for example, 2-0 YY1 is, of course, good. Player 2 is optimizing. But because player 2 accepts anything. But this, for example, 2-0 YY1N is not good because player 2 would reject something she would actually like to have if they play here. They won't go here under this assumption that player 1 plays 2-0, but if they do go here, in this subtree, that would not be an optimum strategy. So, if player 2 does not say yes to the two options, the second and the third option, that's not an optimum thing. She may only say no in the first place because then it's not like does not matter for her. So the only profiles which are left here are 2-0 YYY. Then those are not. This is not relevant because here you have no. This does not happen. It's not good. Here you have no. You have no. You have no. You have okay. y1, 1, and y1 is another one. Yeah, it's no, because you have no here and you have no here. So you have only two subgame perfect equilibrium. When player 1 says I want everything, and then player 2 says okay, anyhow I accept. It's reasonable. You can never say that player 2. Player 2 is definitely not making himself bad in any case. It's always better to have to accept than not. And player 1, given that, player 1 definitely optimizes what she can get. And the other option is the player 2 accepts unless it's to 0. Also, it's always the best for player 2, because she always accepts anything positive. Given that, of course, player 1 won't offer to 0 because then it will not be accepted, but she offers the best thing that will be accepted under this strategy of player 2. She offers 1-1. And the pairs which the players get in those subgame perfect equilibria are 2-0 and 1-1. So they're different. So indeed, there is no uniqueness of equilibria, a strategy profile, and even as even the pairs don't have to be unique. Okay, so let us recap what we've done for the topic of subgame perfect equilibria. We started with a motivational example why Nash equilibria needs a replacement, why it's important to look at what happens at each subtree. Then we actually gave this replacement, which is the subgame perfect equilibria of Selton, and that's the guy who originated that. Then we studied the properties of that thing, we proved that one deviation property, which helped us to prove that the result of the backward induction algorithm is a subgame perfect equilibrium. So, in general, this algorithm does not give us a unique answer. I mean, it has to be this algorithm that we use. I mean, any equilibrium should be possible to get using this algorithm, because each player has to optimize when she acts by the definition of subgame perfect equilibrium, but sometimes this algorithm has many options to act. So in general, the answer is not, it's not. Okay.